This is a reminder class connects. Sorry, this is a reminder class connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate, but please don't share personal information during the class for your own security reasons. So we are on the February 25th attendance ticket. I have 15 green checks so far. Everybody else, please go ahead, give me a green check if you've got it open and ready to go, or if for some reason it's not working, if you have at least written down the password and you're ready to take some pictures of the answers. Looking good. All right, got about 20 green checks now. Love it. Thank you. Remember, if you're having any issues, please let me know. But generally, my solution is to write down the password and finish it a little bit later, okay? Because a lot of times the issues we have are because K-12 is just not working in general. Cool. All right, everyone. So we are on day 19 out of 45. We are officially going to be in the 20s tomorrow. Smiley faces if that makes you happy. Thumbs down if that makes you a little bit nervous because it's going by very, very quickly. Awesome. Good. I'm seeing smileys. Glad we're happy about that. So today we're going to be talking about heat, movement, and energy. So we're going to talk about how what heat energy is and how it moves, go a little bit deeper in that. Tomorrow we'll kind of be applying that knowledge, talking about designing a thermos. What kind of materials would we use to design a thermos? So that'll be your lab for tomorrow. It's a pretty simple lab, so we'll make sure we get that done and knocked out of the park. Friday is technically the end of Unit 5, so Friday we will have a game day to review Unit 5, but you do have an exam that happens after this, so this is still technically called the 5E exam, but just know that it actually happens after we finish Unit 5. But you do have a midterm exam on Thursday. It is not difficult as long as you come to class, so I do go over all of the questions with you in class, so if you come to class, you will definitely be able to get a great grade on that midterm exam, but it's on you to make sure that you meet me halfway and actually come to class on Thursday. And then Friday we will be starting unit number 6. So we've been talking all about energy. We dug really deep into potential and kinetic energy. Now we're going to go ahead and finish up the unit and talk a little bit more in depth about heat energy. So our objective, we should be able to explain what the kinetic theory is and its relation to molecular motion. We should understand what conduction, convection, and radiation are. Define these 3 terms, temperature, heat, and thermodynamics, and also know the differences between insulators and conductors. So there's definitely a lot of different stuff in this lesson, but we are going to do really well on it. We're going to dig deep into it. So heat energy is measured by temperature. It moves matter, which causes phase changes and heat transfer. So let's go ahead and talk a little bit about that. So kinetic theory, what does the word kinetic mean? Tell me again in the chat box. We talk about the word kinetic all the time. So what does kinetic mean? In the chat box, everybody participate. Remember, more participation, the faster we get through everything. Looking good. I see an answer from Taylor. I see an answer from Israel. I see Amanda typing. What does kinetic mean? Awesome. Thank you. I see Miguel typing. Arrow in the chat box. Perfect. Yes, it means motion or movement, something that moves exactly, right? So when we think of kinetic, we should think of motion, moves, movement, right? So what the kinetic theory is, therefore, is the motion of molecules, and this is what causes heat. Okay, so think about everything around you has little itty bitty bitty molecules that we can't actually see. But the way that they're moving is actually what heat is. Smiley face if that makes sense. So heat is actually just the motion of molecules. Whether they're going fast or slow determines the heat of an object. Okay? So for example, when we touch something hot, what's really happening is the object's molecules are moving super, super fast, and so they collide with our fingers that we're touching the object with, and it begins to transfer that energy to our hands. And so for us, that feels very, very hot. And if it's too hot, it can actually hurt ourselves, right? But really what we're feeling is we're feeling the motion of molecules, which is kind of bizarre to think about, that you can actually feel the motion of molecules. So hot objects, what this means is hot objects have a lot of energy, and so they move very, very, very fast. Think about a way to remember it is when you are working out really hard with lots of energy, you're going to feel hotter. Okay, so in the same way, hot objects, the molecules are running around, sprinting around, and sometimes they can move so fast that they can actually escape to become gases. What's this process called where we go from a liquid to a gas? Tell me in the chat box. What is this process called where we go from a liquid to a gas? So for example, on a hot day, you have a puddle of water and then it becomes a gas, begins to disappear. Not really disappear, but it looks like it. Yeah, it's called evaporation. Exactly. You can also do the same thing with boiling, right? If you ever boil a pot of water, how many of you have ever forgotten about a pot of water that you're boiling and come back to a dry pan? Has that ever happened to anyone? I actually use this all the time when I have a pan that I want to dry very quickly. Exactly, Arrow. So if I like wash a pan and I want it to dry very quickly, I try to get rid of as much of water as I can by shaking it. I stick it on the oven or on the stove, turn the heat on for a little bit, and then it immediately dries up because the liquid molecules are getting faster and faster and evaporating or escaping to become gases. Now, cool objects, on the other hand, are going to be the opposite. So they're going to have very, very little energy, and they're going to move very slowly. Think about the fact that ice is a solid and ice has a solid shape, right? It doesn't move. Smiley faces if that makes sense. So ice keeps its shape. It doesn't kind of wiggle around like liquid water or gaseous water, okay? Now, keep in mind, though, that even though the molecules are moving very slowly, they are technically still moving. They're actually, if you were to zoom in, they would actually be vibrating in place. So very, very slowly, but they're still got some movement. If they didn't have any movement, that's what we would call absolute zero, which is the absence of temperature. And that's not possible for us to do physically in our universe quite yet, right? So we might eventually figure out how to do that, but for now, we can't get to absolute zero. Okay, now those molecules, because they're moving so slowly, they can't escape. That's why they stay in their solid form. So what I want you to see is we're going to see the diffusion, which is the spreading of food dye in hot, cold, and warm water. And this should help us better be able to visualize the speed or the motion of molecules in different temperatures of water. Okay, so I'm going to go ahead and pop this up on the whiteboard. It's about 30 seconds. You're going to make observations and give me a green check when you finish watching it. All right, so here we go. Again, green checks when you finish watching it. All right, get me those green checks. Looks like we are finishing up. Looking good, looking good. All right, I'm going to go ahead and share this up on the whiteboard. All right, take a look at this. What are you observing in that video? Go ahead, tell me in the chat box. What were some things that you observed in that video about what happened in warm, hot, and cold water? Go ahead, tell me in the chat box. What were some different things that we observed? Everybody, it's okay if you have the same observation as someone else. It's still good for you to type it down to reinforce your own learning, right? It's not helpful if someone else is learning, but you're not. So make sure you are typing, participating. Go ahead, tell me your observations of what happened. Definitely, right? We've got the hot one right here. Awesome, I see an answer from Stacy. I see Andres. Yeah, so the blue stuff was food dye, so it's just colored water, basically. Yes, awesome. I see Danny typing, Amanda typing, Arrow typing. Let's get some more participation, please. Yolese and Taylor, Razi, Blossom, Parker, want to hear from you as well. Orlando, Nate. Looking good, thank you, Arrow. Awesome, awesome, awesome. I see, let's get Amir typing. Tony, Ashton, want to hear from you. Perfect, thank you, Danny. Awesome, looking good. All right, yeah, I'll definitely go ahead and start talking about these. Keep on typing, keep on giving me your observations, though. So, Stacy, you said the warmest one mixed in the fastest, right? So the food dye definitely spread the fastest in the hot one. If you take a look right here, the food dye is almost completely mixed in, right? So yeah, Andres, it almost looks like it's melting. It's not really melting because it's still a liquid, so it's still a liquid in a liquid, but it is spreading out a lot faster. Yeah, and Stacy, it definitely happened the slowest in the cold water, right? So let's see here. Yes, arrow, we can see it takes different times depending on the temperature, right? The hot one was fast, the cold one was slow, okay? And the warm one kind of moves around a little bit more, right? So the warm one is halfway in between, so we can actually see it move around, right? The cold one didn't move very much, right? And then let's see here. I think I got everyone's. Awesome. Thank you. Yes, Amanda. Perfect. Okay, so we can see that which molecules are moving the fastest. Okay, no worries, Taylor. Which molecules are moving the fastest? Warm, hot, or cold? Based on what we saw with the food dye, which one must be moving the fastest? Yeah, the hot molecules are absolutely moving the fastest, and the cold ones are therefore moving the what? Hot ones are the fastest, cold ones must be the slowest. Yes, those ones are absolutely the slowest. Perfect. All right, so that should help you better understand the motion or the kinetic movement of molecules. Smiley faces if you feel like that was a good example, if you can visualize it a little bit better. Cool, cool, cool. All right, so now here's the thing. We measure temperature all the time, right? Think about, tell me in the chat box, what's the current temperature of where you live? What's the current temperature of where you live? Sorry, excuse me. Tell me, what is the current temperature of where you live? Awesome. Yep, 56 degrees, 50 degrees. It's a little bit chilly, right? Hope a little bit warmer by you, 60. Amanda, you're like, it's just cold. It is just cold. Okay, here's the thing though. Temperature is actually, oh, it's going to rain. No. Temperature is actually what we call an indirect measurement. So temperature is not a perfect measurement of total amount of heat, okay? Because what it's actually doing is it's actually taking the average amount of energy that each particle has. I know, I'm sorry, I'll let you down in a moment. I'm just trying to get you undone here. Okay, so it's not the same thing as total heat. It's actually an indirect measurement. So let me go ahead and explain this to you. So which group do you think is going to be happier? Okay, so these are a bunch of dog-loving groups, okay? The first group is 100,000 people that only have 500 total dogs versus 100 people with 500 total dogs. If these guys are dog lovers, which group do you think is going to be happier, A or B? Go ahead, use your polling tools and tell me which group will be happier, A or B. 100,000 people with 500 dogs or 100 people with 500 dogs? Awesome. Use your polling tools. Yes, I see lots of answers popping up. Okay, awesome. Gonna go ahead and publish these up on the whiteboard. Looking good. All right, looks like most of us are saying B, and if you said B, that is definitely correct. The dog-loving group down here is definitely going to be happier. Now, think about this. How many dogs on average do each of these people get? So 100 people, 500 dogs, how many dogs does each person get? Go ahead, tell me. Yeah, that means that everybody would get about 5 dogs, which if you're a dog lover, that's definitely super, super exciting, right? So you have 5 dogs. That's awesome. On the other hand, for group A, in order to figure out how many dogs each of these people would have, we would have to go ahead and divide the dogs among the people. So let's go ahead. I'm going to share this with you. All right, let me grab my calculator. All right, here we go. So what we would be doing is we would take 500 dogs and divide it by the 100,000 people. So on average, each person gets how many dogs? On average, each person only gets how many dogs? Take a look at our answer here. We divided the number of dogs by the amount of people. Yeah, you don't even get 1 dog, right? You get 0.005 dogs. Not that we're going to be splitting the dogs in half, but that means that really only one person in, like, only a few people for every 100 or so people are going to have a dog. Smiley faces if that makes sense, right? Yeah, maybe you get like a toenail or something. Yeah, so they're definitely not going to be as happy. So the same thing is true with heat, okay? Imagine that the dogs are heat, okay? Units of heat, right? So if you have a really, really big population and a really, really small population that both have the same amount of dogs or the same amount of heat, Okay, the average is going to be different. Okay, so for a big bucket of water that gets 50,000 joules, it's only going to feel like warm water, right? In the same way that our big population here is not going to be very happy, right? Because they don't get a lot of dogs for each person. Okay, or in this case, they don't get a lot of heat for each molecule. Whereas down here, if you have a really small cup of water and you add 50,000 joules of heat, it's going to feel super hot, just like our happy population here, because they get lots of dogs per person, or in this case, they get lots of heat per molecule. Smiley faces if that makes sense. Smiley faces if that makes sense. Andres, make sure it's all lowercase and make sure that you're spelling it correctly, all one word. Okay. If it's still not working, you can email me and we can figure it out after class, okay? Perfect. All right, so again, temperature is indirect, right? It measures this average over here, not the total amount, right? So this right here would be the total heat. Okay, it would be 50,000. Yeah, Andres, if you... Whereas this over here is the temperature, the temp or the average. Okay, and so the average can change. Awesome. Good, Andres. Cool. All right, let's go ahead and keep on going. So now we're going to talk about what our subject is. So our subject is what we call thermodynamics, which thermodynamics is the study of heat and its movement or change. So let's go ahead and talk about this. So we can see here thermo. Thermo sounds like thermal underwear. Do we remember thermal means what? Thermal means what? Tell me in the chat box. If we know thermal is like thermal underwear, yeah, it means something warm, right? So in this case, thermo means heat, right? So we're going to go ahead and this is going to be heat. And if you think about someone who's a super dynamic talker, think about the fact that they're always moving their hands, right? Someone that just stands there and doesn't move their hands is not super dynamic. So in the same way, thermodynamics is talking about motion. Again, okay, so kind of like kinetic, but a little bit different. So thermodynamics is the study of heat and motion. Keeps you warm. All right, smiley faces if that makes sense. Again, scientists aren't super creative with their naming, so they try to make everything as obvious as possible. Cool. Now, remember, this idea of heat moving relates back to our conservation of energy. So conservation of energy states that energy is never created and never destroyed, right? The total amount of energy in the entire universe has always been, is, and always will be the same amount. But when we say something like, oh, we lost heat energy, think about your house, right? If your parents are like, close the door, we're losing heat, all right? Heat energy is never actually lost. Instead, it's just moving or changing into something else. Thumbs up if that makes sense. It's just moving or changing into something else. Yeah, exactly. So you can be like, Mom, heat is never lost. It's just moving. Calm down. All right. So, for example, when you boil water, right, that heat energy is not just disappearing from the stove, right? Think about the fire from the stove. It's not just disappearing. Instead, it's going into the water, it's being transferred into the water, and it's beginning to speed up those molecules until they turn into steam. So again, that heat's not being lost, it's just beginning to move to a different place. Yeah, exactly. So you can see that here, right? It just begins to move and turn it into gas. Cool, let's make sure all of this makes sense. Go ahead, grab your whiteboard tools. Please use thin lines. It's kind of cramped, so make sure you use thin lines, and you can use any color you want, but match up the terms on the left with the definitions on the right. Go, go, go. I will point out that one of these definitions has the word theory in it, just as a hint. I know kinetic theory and thermodynamics do sound similar, but they're a little bit different, Awesome, awesome, awesome. Get your answers up there. Give you another 10 seconds. I know, it's kind of all over. That's okay. That's how we learn. Yep, double check temperature. I need a few more answers on temperature. Looking good, looking good. All right, let's go ahead. I'm going to pause your tools. Let me actually get my tools ready here, and then I'll pause yours. Awesome. All right, pausing them now. All right, let's take a look at this. We're a little bit all over the place, so I want to make sure that we really understand this. You guys are not terribly off base, though. A lot of it is because they do have very similar definitions. So kinetic theory. Kinetic theory is a theory, so I'm going to go with the one that says theory, and it's the theory that the motion of molecules causes heat. Remember, the word kinetic means motion of molecules, right? So kinetic theory should actually be this one, okay? Now, temperature. Right, temperature is can be cold or hot, right? So this idea of molecules having a lot of energy and moving fast, that would be hot, right? So that wouldn't encompass all of temperature. Instead, what temperature is again, it's an indirect measurement of heat. It measures average kinetic energy, or in our case, the average amount of dogs in a population, right? That was our example. So temperature is an indirect measurement. Now, thermodynamics is going to be the science, the name of the science, which is the study of heat and its movement or change. Remember, thermo means heat. Thermo means heat. And let me go ahead and change my colors here. Last but not least, we got this, right? Hot objects have fast-moving molecules. They have lots of energy. Cold objects have very little energy, and they're moving very, very slowly. Tend to be things like solids. Smiley faces if those corrections make sense. I know we started off a little bit off balance, so I want to make sure all of that makes sense. Cool. All right, everyone. This is actually number 1 in your ticket. I'm going to go ahead and give you 60 seconds to work on that. Give me a green check when you have it saved. Go, go, go. All right. Sorry about that, everyone. Had to put my daughter down. Go ahead. Give me some green checks. Amanda, Amir, Danny, Donovan, Dorian, Dree, Dylan, Edwin, Elliot, Jaime, Jackie, Maxine, Blossom, Nate, green checks. Looking good. All right, everyone. Again, if you need the ticket, here it is in the chat box. Awesome. Let's keep on going. All right, everyone. So the last thing that we need to talk about is the 3 different ways in which heat can actually move. Okay, no worries, Amanda. Just make sure you have the password saved in case you lose anything. That way you can go back to it, okay? All right, looking good. So let's go ahead and talk. Okay, Danny, no worries. Just if I'll know that. That's okay. Thank you for letting me know, though. Okay, so let's talk about the 3 ways that heat can move. So first of all, heat only ever moves from high temperatures to low temperatures until both objects are actually the same temperature, which we call thermal equilibrium, right? Thermal meaning warmth, and equilibrium, what does this word look like? What word do you know that sounds very similar to equilibrium? Tell me in the chat box. What word do we actually already kind of know in here? Yeah, equal, right? It's until they are equal in heat. Okay, so that being said, if you have the same amount of 0-degree water and the same amount of 100-degree water and you mix them together, you're going to end up with a bunch of 50-degree water. It just equalizes out until it's halfway between the 2 temperatures. Smiley faces if that makes sense. Smiley faces if that makes sense. Okay, it equalizes between the 2. Okay, now again, this is really important that heat actually goes only from hot to cold. So really, cold is actually not a real thing. Cold is actually the absence of heat. So how many of you have ever heard your parents say, close the door, you're letting the cold in? How many of you have heard a parent say that? Close the door, close the window, you're letting the cold in. Okay, now if they tell you that, you could be like, that's not true, Mom and Dad. You can actually only let heat out. Yes, so, right, close the window, you're letting the cold in. Not true. Thermodynamics says that heat actually goes out. So there is no such thing as cold. Cold is just the absence of heat. So the first way that heat can move is what's called conduction. And conduction is the one that you're probably most familiar with, because if you've ever picked up something that's hot and felt it burn yourself, that is conduction. So conduction is the movement of heat when molecules are actually touching, okay? So molecules are going to collide with an object that they're touching, and you're going to feel it as heat. So take a look here. If you have some hot coffee and you stick a metal spoon in it and you wait for like 3 minutes and you go back and try to touch the spoon, what does the spoon feel like? Tell me in the chat box. If we have a really hot coffee, stick a metal spoon in it, grab it with our hand a little bit later, how does the metal spoon change? Yeah, it gets much, much hotter, right? Muy caliente, exactly. All right, so let me go ahead. I'm going to show you a quick demo of this. Sorry, Fet. Give me a smiley face once you can see my screen. Awesome, good. All right, so let me go ahead and jump into this. Okay, so here I have two objects. I have a piece of iron and a piece of brick, and I'm going to actually show you, you can see their energy, right? So iron currently has a few more energy molecules, I guess, energy units than the brick does. But here's what's going to happen. We're going to actually go ahead and heat up this iron until it's super, super hot. You can see it's getting more and more energy, getting super, super, super hot. Smiley faces if you can see that. Again, I know there's always a little bit of lag, but you can see there's lots of heat energy in our iron now. Cool. Now what I'm going to do is I'm going to go ahead and grab the brick and drop that on top, and I want you to tell me what happens to the iron versus the brick. All right, let's go ahead, drop that on top, and tell me, what do you see happening? Yeah, the brick got much, much hotter, right? You can see the energy units from the iron went into the brick. So the brick got hotter, but the iron did what? The brick got hotter, but the iron actually did what? Gained energy, but the iron, no, it didn't quite say the same, right? Where did the brick get the energy from? If the brick got energy from, it must have come from somewhere. Remember, conservation of energy says that you can't just magically create or delete it. Yeah, the iron lost the heat, right? The energies actually went from the iron to the brick. So the iron got colder and the brick got warmer until they were the same temperature. Smiley faces if that makes a little bit more sense. Again, this is conduction where they're actually touching. Okay, the objects are touching each other. Awesome, cool. All right, jumping back over here. So the next one that we want to talk about is convection. So how many of you have what's called a convection oven, or have you ever heard the term convection oven? Go ahead, tell me in the chat box. Have we ever heard that term, convection oven? Yes, no, what do you think? Yeah, awesome. Okay, sorry, I'm just gonna get this. Cool. All right, so convection, what this actually means is your convection oven actually has a fan in it. And what that does is it causes the air inside of the oven to circulate, resulting in more even cooling. Okay, so think about if you just had an oven where it just had a single place where it heated, you would end up with like pies and food that ended up very unevenly cooked, right? The back of your food would be much, much hotter and more burnt than the front of your food. Right? Exactly. So it's really recommended to use convection ovens because it spreads out the heat. Okay? So when you think of convection, you should think of a fan, like in a convection oven, that makes air circulate around. Smiley faces if that makes sense. Okay? So conduction means touching. Convection, we remember, convection is different because it's like an oven with a fan, making things circulate and swirl. Cool. All right. So convection ovens, what's really happening here is you can actually have convection even without a fan. So in reality, what happens is fluids that are heated get much, much less dense. How many of you have ever heard the saying, hot air does what? Hot air. Tell me in the chat box. Hot air. Do we know? Yeah, it rises, exactly, just like a hot air balloon will rise because it's air that's being heated up. Okay, smiley faces if that makes sense. That's why when it's really, really hot in the summer, it's nice to go to lower floors because they're cooler because all the hot air is going up. Okay, so hot air will rise when it gets heated. Okay, it gets hotter, it rises up. The cool air, on the other hand, as it cools off, will begin to sink. And as you can see here, as hot air rises and cool air sinks, it begins to make these swirls, okay? It depends on the material that the balloon is made out of, right? And it's also not like you're applying the flame directly to the material. You're only applying the flame to the air, which air is actually a pretty good insulator, and so it's not going to spread the heat to the actual material as much. Okay, that's a good question though. All right, so as hot air rises, cool air sinks, it circulates, it goes around in circles and circles and circles, and this causes what are called convection currents. And this can actually also happen in things like water. So when you are heating up water, the same thing is happening. Hot water rises, cool water sinks, and it begins to circle, circle, circle until it is more evenly spread out. Again, fluids are spreading out these this heat, okay? So let me go ahead, I'm gonna show you this really quickly, this idea of a convection oven. All right, so here we go. All right, so you should be able to see this. All right, so you can see here, convection oven, right? You can see that heat is coming out of one area and then swirling back in, right? So this is what a convection oven does. Again, you should think convection currents or swirling. Okay? Yeah, that's why bubbles come from the bottom. Exactly. Smiley faces if that makes sense, everyone. Smiley faces if that makes a little bit more sense. Cool. All right, now radiation is kind of a special one. Radiation actually does not require matter in order to travel. So radiation is the travel of heat without using things like atoms or molecules like the other two, right? Convection and conduction required matter, right? Conduction requires objects to be touching, so molecules need to be there to be in contact. Convection requires fluids like air and water, both of which are made of molecules, okay? Radiation, though, is special. Radiation does not require matter. Instead, it gets carried by what are called electromagnetic waves, okay? So this is super important because remember, is there any molecules in outer space? Are there any molecules in outer space? Tell me in the chat box. No, there aren't. So if there were no molecules in outer space and there was no way for heat to travel through outer space, then sunlight, the heat from the sun, could never actually reach us. Smiley faces if that makes sense. If this was not true, sunlight could never reach us and warm the earth, okay? So radiation is special. So the radiation from the sun can actually travel through outer space where there's nothing there, very, very special, and still reach Earth in order to heat the Earth up. Okay, the same thing happens when you're next to a fire. Even if the fire, even if you're not touching the fire, you can still feel the warmth from the fire. Okay, let's make sure that this makes sense. Go ahead and match these up. Grab your whiteboard tools, match these up. It could be Andres. There's actually a lot of stars that you see that have actually died. They've actually burned out, but because light takes so long to travel, the light is still traveling to us even after the star has been dead for billions of years. It's pretty crazy to think about. Same thing with our sun. If our sun went out, A, that'd be really bad, but B, it would take 8 minutes before we stopped seeing the light from the sun. Cool, all right, everyone, let's go ahead and take a look at this. Yes, conduction is going to be the collision of molecules that transfer heat. Convection, just like an oven, the warm fluids rise, cool fluids sink, creating currents, convection currents. Radiation can travel without matter. This is number 2. Go ahead and take 30 seconds. Give me a green check when you have this answered. Go, go, go. Go ahead, give me green checks. Yeah, so Andres, it might not have actually been a star that you were looking at. There are a lot of satellites that look very similar to stars. That will sometimes blink, right? I mean, it could be aliens, but I feel like we might that might send some waves through the astronomy community. Yeah, so the sun can actually go out. Keep in mind the sun is producing energy based on chemical reactions, nuclear reactions, which are a type of chemical reaction. And once that nuclear reaction runs out, then the sun will run out as well. Cool. All right, everyone. So I'm going to go ahead and skip up to this. Let me go ahead and finish this really quickly because I know we're almost out of time. So here's the thing. All materials will eventually conduct heat, okay? Dylan, I can go back to it later or you can find it in the recording, okay? But we need to finish because I've only got 1 minute left to go through all of this, okay? So all materials will eventually conduct heat. However, there are some materials that conduct it much faster and some that conduct it much slower, right? So conductors will speed up heat transfer. They get hot much faster. Insulators will slow it down. They get hot much slower. So for example, think about when you are stirring a pan of hot liquid on the stove. Do you want to be using a wooden spoon or a metal spoon? Which one slows down heat transfer to your hand? Which one would you rather be using? Which one would you rather be using? Yeah, definitely. You would much, much rather be using a wooden spoon. Danny, it'll load for you eventually, okay? So metal conducts much better, and so it gets hot much faster than wood. Smiley faces if that makes sense. Smiley faces if that makes sense. All right, cool. Let's go ahead and fill this out really quickly. So an example of a good wood, is wood a conductor or an insulator? Tell me in the chat box. Is wood a conductor or an insulator? You have a little hint down here too. Is wood a conductor or an insulator? Yes, wood is going to be an insulator, absolutely. Sorry, I'm going to change my color here. Right, so wood is a good insulator. And does that mean it slows or speeds up the transfer of heat? Again, think about stirring with a wooden spoon. Are you going to get heat to your hand slow or fast? Yes, it's going to slow it down, absolutely. An example of a good blank is aluminum. What would aluminum be? Pencil has both wood and metal in it. That's why it's in both. Yes, aluminum is a conductor, and just like if you're stirring with a metal spoon, are you going to feel the heat slower or faster? Slows or speeds the transfer of heat? Yeah, graphite is yeah, there's no lead in pencil. It's just called pencil lead. Yeah, it's going to speed it up. Okay, this is number 3 in your ticket. Go ahead and give me a green check when you have it saved. You can also take a picture of this and give me a green check. I'm only going to give you 30 seconds, but I do need to go to my next class. So please go ahead and give me a green check really quickly, letting me know you've got it. Awesome. Go, go, go. 10 seconds. All right, Amir, Ashton, Donnie, Dorian, Dree, Edwin, Ethan, Israel, Jaime, Martina, Maxine, Michaela, green checks, please. Looking good. All right, everyone. So sorry, I know we're finishing up quickly. Here is your quiz for today. Remember that your attendance ticket does have all of the answers to the quiz, so that's super easy. Go ahead and just do them side by side and then submit them at the same time. And then here's your last word. Thanks so much, everyone. I will see you later. If you missed anything, it will be in the recording, but I do need to go. So go ahead and please log out. Bye, everyone.